All right, this is a look at the role conservation of momentum plays in collisions between objects. Just to recap, momentum is a vector quantity. The fact that it's a vector is important, and it measures basically the amount of motion an object has, which can be thought of as how hard it is to stop an object in motion. The letter for it is lowercase p, and it's equal to the mass of an object times its velocity. Now, an object can change momentum, so it can have a change in momentum if an impulse is applied, which means an outside force acts on the object for some time. However, if there's a system that consists of one or more objects, in this case, the objects in the system apply forces on each other. These are internal forces. So it takes an external force to change the momentum of a system. So in a collision where there's only internal forces, there'll be no change in momentum for that system. Conservation of energy is often used to solve questions. When it comes to the case of collisions, energy is not usually conserved. If I look at the car crash here, you'll have a lot of energy lost to heat and sound when the cars collide. So kinetic energy is usually going to be lost in a collision, but in any collision where there's only internal forces, momentum will be conserved. Now, there are collisions where kinetic energy and momentum are conserved. Those are called elastic collisions. What I'm going to look at here are going to be inelastic collisions where momentum is conserved, the kinetic energy of the system is lost in the collision. When analyzing questions involving collisions, conservation of momentum is going to involve setting the total momentum of a system before the collision equal to the total momentum of the system after the collision. For example, a scenario involving conservation of momentum could look something like this. So here I have a car and a truck that are colliding head-on, and then after the collision they go in opposite directions. In both cases, I'm adding the total momentum, m and v, before and after the collision. Now, you always add momentum when doing conservation of momentum. However, since momentum is a vector, once you define a positive direction, the velocities here can be positive or negative. So I'm going to do 4 questions here that involve collisions. The first one, example A, is not really a collision. It's called a recoil, or also a superelastic collision, because this is a case where there's an internal force. The objects are not moving. In this case, the objects are Mario and Luigi. And then afterwards, they're moving in opposite directions. Because momentum is a vector, it can be conserved here. It's a bit strange that the initial momentum is going to be 0, but that 0 momentum is conserved. The way that that's possible, again, with momentum being a vector, is that after the collision, they're going to have momentums that cancel out, which means they have an equal magnitude, but act in opposite directions. All right, so conservation of momentum says that the initial momentum total equals the final momentum total. And before the push, nothing is happening. So the initial momentum is 0. And then after the push, I just add the momentums. Momentum is mv of both Mario and Luigi. Now I have to pick a positive direction here. So I'm going to say to the right is positive, which means that after the push, Mario's velocity will be negative since he's traveling to the left. So I'll write the mass of Mario, which is 80, times his velocity, which is -6, plus the mass of Luigi, which is 60, and I'll just call his velocity v, and those have to add to 0. When I solve that, I'm going to get positive, which means he's moving to the right, 8 meters per second. Now, if I go ahead and solve mv for either one, I'll get that Mario has a total momentum of -480 kilograms meters per second to the left after the collision. And then Luigi has a momentum of +480 kilogram meters per second to the right after the collision. So here, even though the initial momentum was 0, it's still conserved because after they push, their momentums cancel out and add up to 0. Example B still involves Mario and Luigi. In this case, they're driving carts. So Mario is going at 24 meters per second. He has a mass of 150 kilograms. Luigi, who has a mass of 100 kilograms, is initially going slower. And then after the collision, Mario slows down to 12 meters per second. And the question is to find Luigi's velocity after the collision. So conservation of momentum, total momentum before equals total momentum after. In this case, they're moving before and after the crash. So I have mv for Mario before the collision plus mv for Luigi before the collision would equal mv for Mario after the collision plus mv for Luigi after the collision. And I want to find Luigi's final velocity. So I'll go ahead and write down my expression here with the numbers plugged in. And there's what that looks like. All the given velocities are to the right, so all the velocities that I plugged in here were positive. And then when I solve that for Luigi's final velocity, I get that his velocity v equals, he's still going to the right, so this is also positive 26 meters per second. So I would say Luigi's speed after the collision is 26 meters per second to the right. Example C still deals with Mario Kart. So in this case, I have Donkey Kong, mass 150, colliding head-on with Toad, who has a mass of 50. Donkey Kong's initially going at 12 meters per second, and then Toad's going at 6 meters per second in the opposite direction, so that'll have an opposite sign of velocity. And then after the collision, Toad is going the opposite direction of his initial velocity at 8 meters per second. And then it's to find Donkey Kong's velocity after the collision, which is going to include here both a direction, which is unknown, and a magnitude. All right, so conservation momentum, initial momentum equals final momentum. Now here I have to be careful with signs because they're going in opposite direction. So I have east and west as the directions here. So I'm going to say that east is positive, which means then that west is negative. And then I'm trying to find Donkey Kong's final velocity. If that final answer is a positive number, I know that he's going east after the collision. If it's a negative number, then I know he's going west after the collision. When I plug in numbers here, I have to be careful with Toad's initial velocity. He's going to the left or west, so I'm going to call his velocity negative. And then I'll go ahead and plug numbers into conservation of momentum. And here's what that looks like. So my eastern velocities, which was Donkey Kong's initial velocity, and Toad's final velocity were positive. And then Toad's initial velocity was to the west, so that's negative. And then when I solve for v, I get that Donkey Kong's final velocity here is going to be positive, and then it's 7 1/3, so I'll write 7.3 meters per second. And that velocity is to the east, which was defined as positive, so I'll say Donkey Kong's final velocity is positive 7.3 meters per second eastward. In the last case here, I have two objects that stick together. When two objects stick together in a collision, that's called a perfectly inelastic collision. So I have a cart that's 2 kilograms traveling to the right at 8 meters per second, when it's going to collide and stick to a 6 kilogram cart, and then they're going to move off together, and the question is to find the combined velocities once that happens. All right, here I have momentum before equals momentum after. Now momentum before is just based on the first cart, so the momentum before they collide is going to be that cart, its mass times its velocity, so that's going to be 2 kilograms. And it's moving at 8 meters per second. And that'd be plus 0 for cart 2. And then afterwards, I'm still going to have one momentum, so I'm going to have a combined mass, which is 2 kilograms, plus the other cart's mass, which is 6 kilograms. And then that's going to be times the velocity of the two combined carts. And when I solve for the velocity here, I get 2 meters per second. And all the numbers here are positive, so that velocity is also in the way the first cart was moving, which is to the right.